So let me start by thanking you again for accepting this invitation, especially on a short notice. And Will Hartley is a postdoc, right, in UCL, and he's been working on DS, and especially matters of photometric redshift and galaxy evolution. And, well, he will tell us more about it. So please, Will, go ahead. Thank you.
Thank you. So thank you for the invitation to speak to you. It's the first full-length webinar that I've given, so this is kind of a new experience, a great way to do seminars across continents, I think. So I'm going to talk a little bit about PhotoZ, particularly in the context of the dark energy survey, but this is relevant to other dark energy experiments that are ongoing or coming up as well. And although PhotoZ can be a bit of a dry subject, it's actually shaping up to be one of the most important limiting factors in exploiting the new surveys for cosmological information. So hopefully you'll find something valuable in here. So a quick overview of what I'm going to talk about. I'll do a very brief introduction of the principle of PhotoZ because I expect most people are well aware of how to go about this. Then I'll discuss the most simple failure mode of template, or I prefer the word model PhotoZ because really what we're doing is trying to model the galaxy population as well as the individual galaxies. So I'll talk a little bit about what's going wrong. A brief aside, I'll discuss the danger of doing ad hoc corrections as are quite popular in galaxy evolution, such as photometric corrections. Then I'll cover where we are up to in the dark energy survey in the context of model PhotoZ, in particular the BPZ case that we ran in the science verification analysis that was presented in Bonnet et al. 2015. And then I'll go on to the next steps, what we need to do in the future to improve the model PhotoZ in terms of the templates and the priors. And then finally I'll try and end on something of a positive note with a case study of red magic, which is not something I've been directly involved in, but I want to show how these things can come together and produce something that's actually that's quite powerful. Okay, so cosmology, almost all the observational methods we use to derive cosmological constraints require that we know the distance to a set of probes. So in particular, things like the baryon acoustic oscillations and weak lensing require known distances or reasonably estimated distances to a very large number of galaxies. And with spectroscopy this is very easy, as you can see from here. This is a stack of 1,000 or more galaxies from the UKIDS UDS-SED survey. And we have all of these beautiful features which nail down the redshift very precisely, and so we can get the distance to it. But spectra such as these are really limited to relatively small samples. I mean, well, small in the modern context. So even Sloan is well, roughly 1 million, Vipers 100,000 or so. But really, because the information content in each individual galaxy in weak lensing is so low, we really need tens, if not hundreds of millions of galaxies to get cosmological useful information out of it. And so we can't rely on spectroscopy anymore. Instead, what we try to use is the information not in emission lines and absorption lines, but in the shape of the continuum of the SED itself. So in broadband photometry, we have a kind of a smoothed, sparse sampled representation of the SED, and we have to try and access this information to understand the distance to all these hundreds of millions of galaxies. And there are two kind of broad basic ways that we can approach this problem. The first is the so-called template or model PhotoZ, where we have a set of photometry. In this case, we're in what you might call the data-rich regime. We have 11 broadbands, each of them very deep, and then we try to fit a model of what we think the underlying SED of the galaxy is to these photometry, and we come out with something that's a very nice fit in this case. So we get a fairly precise redshift in this way. The alternative is using some more modern methods, machine learning in particular, to directly access the mapping between the colors that galaxies have and the redshift at which they're at. So in the upper panel here, I have a sample of galaxies that have known spectroscopic redshifts, very secure spectroscopic redshifts from emission and absorption lines, etc. And they're in a color plane, so G minus R and R minus I. And then below you can imagine how you would imprint this color distribution onto this unknown set and thereby get a decent estimate of the redshift of any of the galaxies in the lower panel. Now, template or model redshifts are often considered more of the traditional method. I guess this comes partly from our bias of most people coming into this from physics. We like to know physically what's going on. And also we don't like the idea that we're just feeding data into a black box and getting an answer out. So there's certainly in galaxy evolution there's been a bit of a resistance to using machine learning PhotoZ, but as I'll show in a moment, they're really coming of age. However, they're unlikely to be sufficient for the current and future surveys. So to give you a sense of what we need, here are a couple of the ongoing and planned cosmology experiments. So the DES, the one that I'll be mostly talking about today, we have 5 bands, G, R, I, Z, and Y, and the principal depth of this is characterized by the I band, so less than 24, and is pretty flat across the photometry actually. So this is 10 sigma detection limit. And we require for the set of probes that are using in weak lensing, because it's really weak lensing that is driving the requirements on the redshifts, a bias in the mean redshift of the galaxies that are used in any given tomographic bin are of 1% or less. So this is quite stringent, as we'll come together a little bit later. There's also a target accuracy on the scatter. So these targets were designed or intended when the surveys were in an early kind of conceptual stage, and at that point we were really talking in terms of point redshifts, so the best estimate that we can give to any one galaxy. So in this case the scatter makes sense, as this is the kind of dispersion. This 0.12 is actually quite generous, so this is a fairly loose requirement on the uncertainty in the population, but the mean is the one that really needs to be close. And in Euclid, well, so Euclid has JH and YJ and H, and then a visible band, but it's also going to make use of ground-based optical photometry such as DES, perhaps LSST, and so we can expect to have something like 8 bands to a limit of 24.5 in the visible. But here the target accuracy on the bias is now 0.2%, which is incredibly stringent. And so this is going to be a really tough requirement for the future. And just to give you an idea of the context, so deep extragalactic fields where we have 11 bands in the Euclid ODS or even 30 bands in Cosmos, typically the thing that galaxy evolution people care about is the scatter on the redshift. So we want to get the individual redshifts as close to their true value as we possibly can, and we get that to around 3% in the UDS and 1% in Cosmos. But the bias is largely not optimized for, and in some cases not even measured. So the even state-of-the-art galaxy evolution surveys don't necessarily meet the requirements that we're asking for cosmology experiments, despite being far more blessed with data. Okay, so in the DES science verification data, so this is before we've even begun the survey, we already took a look at how the PhotoZ were performing, and this is based on the point redshifts and whether they meet the criteria that we set. In this plot you see this sigma 68, this is the scatter on the y-axis, and then the mean bias for the whole sample on the x-axis, so not using tomographic bins here. And the sample, the symbol in the plot gives you, corresponds to different types of machine learning type method or trained methods. The circles are ones where templates or model methods were used. and then the squares are ones where a P of Z is returned. Well, you can see from the other points which ones of the squares actually correspond to models and which ones from training or machine learning approaches. But the important point here is that all of the best performing codes, those in that little inset box, are of the machine learning type. Now, this is kind of a biased test because the samples that were split, so we have, for a machine learning approach, we need a training and then a validation sample. So we use a set of spectroscopic redshifts to train the machine, and then we see how well it's doing on the validation machine. And these were almost perfect mirror images of each other. So we expect that machine learning methods would do well here. But there is exactly the same information available to the template fitting codes, and so there's still this question of why they're not performing as well as the training methods. And so to understand this, we want to look at where the failures are occurring. And I should note that in a data-rich regime, template codes do extremely well. As I said, these have been used for many, many years, and in fact with galaxy evolution studies, they're the only option, just because of the lack of spectroscopic redshifts to train the galaxies. But because they've been very good, there's really been no need to make vast improvements to the modeling methods, something which cosmology experiments are now driving. So that's kind of the essence of this talk. And one more caveat before I move on to look at some of the problems and how we can approach them. And this is a caveat for the whole of PhotoZ, but in particular for machine learning. So machine learning methods require spectroscopic samples with which to train, and obviously all of PhotoZ needs spectroscopic samples to validate, although there are some other methods in the pipeline as well. And the figure here shows shows the incompleteness that we have in one of our best spectroscopic surveys to date. So these are data from the BBDS DEEP survey. This was I-band selected down to I of 24, purely magnitude cut, no further color cuts. And the symbols here show you the completeness that you get in different bins of I-band magnitude and in color space. The symbol corresponds to how many targets were in this particular region of color space. So this is broken up by a k-means clustering algorithm. And the important thing to note here is that even at bright magnitudes, even at I of 22, with 4 hours on an 8-meter telescope, we still have incompleteness. In some cases, quite severe incompleteness. And as we go to the depths that we need to probe in order to do the weak lensing analysis in the final DES data, things become pretty hopeless, actually. It's difficult to find samples where the completeness is 50% or higher. And so, really, we have no way of currently validating the redshifts that we're trying to use, and we are yet to understand the biases that this incompleteness is impacting upon the PhotoZ of machine learning methods. And so the short of this is that the modeling approaches to PhotoZ will have to work for this and future surveys, because we cannot rely purely on machine learning methods unless we have a complete spectroscopic sample to train them with. And certainly down to the depths of Euclid, this does not look like it's going to happen anytime soon. Okay, so where are template codes failing? This is one of the worst plots that you will see. For anyone who's run template codes, they will know that we don't use this standard of a PhotoZ solution actually in any analysis at all. This is to kind of give you a sense of where we're starting from and where we need to build from. So this is a raw chi-square, so you can take any template code you like, run it through with a set of 7 empirical templates, and compare the output PhotoZ with the spectroscopic redshift using the DES bands, that's G, R, I, Z, and Y, although actually the Y doesn't give us very much information at all. And you can see these horrible wings that show a degeneracy between redshifts 0.2 and 0.6, so both on the high spectra, low photometric side, and vice versa. And so this is showing us one of the main problems in the template codes to begin with. And so we want to understand where these problems are coming from, how we can eradicate them, and whether that gives us better results in the end. When you look at the templates or the colors in the templates around these two redshifts, so here are various interpolated templates between this basic set of 7 for redshift, a slim redshift interval between 0.25 and 0.55. You see that there's this clear space where they overlap in the middle. And so this is what's, in essence, the degeneracy that we're seeing in these wings. And here it is put in another way. So in black, you see a kind of an elliptical-like template at low redshift, and in red, there is a star-forming like template at slightly higher redshifts. This is the 0.6 version. And when you integrate the filter over each of these templates, then you find that the photometry lie, or the expected photometry, lie almost on top of each other. If we plot the actual photometry, then the G, R, I, Z and Y band lie, well, exactly where they're predicted to be. And I've also included the U band data at just short of 4,000 angstroms. And you can see that this completely solves the degeneracy. So this is why galaxy evolution studies have never really had to worry about this, because they almost always include a U band in the data sets that they produce. So if we had U band, everything would be better, right? And this is true. So this is the same raw chi-squared, so there's no prior, the same templates as before, but now including U band data. And the degeneracy is almost completely eradicated. So when I first looked at this, I felt that, well, we were kind of stuck without getting U band data, that actually we needed to think about the entire survey strategy again, and maybe incorporate this extra band into the survey somehow. But when we look at the machine learning methods, actually we find a slightly different tale. So here I've run Huan Lin's DES-DM code on the same data. These are the DES bands using mag-auto and mag-det model magnitudes. So these are two different estimates of the total magnitude for the galaxies, again using G, R, I, Z and Y, so no U band in here at all, and there's no sign of the degeneracy that we were finding with the template codes. And I thought, well, okay, there's extra information coming in here. So there's a correlation, of course, between the magnitude of a galaxy and the redshift, and also perhaps there's something between the auto and the det model magnitudes that's giving some extra information, such as the shape of the light profile. And so I ran it again, but this time just using colors, just using mag-auto colors. So there is no more information here than is accessible to the template code using the basic chi-squared method. And yet we still see the same thing. We see that there's no degeneracy at all. And so this is not a simple case of there being too little information for the template code. It's actually that it's the templates that are the problem, or somewhere in the methodology of the modeling in the code that's causing this degeneracy. It's not intrinsic to the galaxy population. Okay, so what are the most likely causes of this particular failure? The first is the lack of a suitable prior. We could have photometric 0-point calibration errors, or maybe we're using unphysical templates, or the final possibility is that there actually is a degeneracy and it's simply hidden in the machine learning methods. Now I don't believe that one's the case, so that's why it's in brackets. 1 and 3 there are essentially different ways of describing the fact that the model that we're inputting into the code is poor, is not up to standard. And so I'll come on to that shortly, and that's most of what I'll be talking about. But just as a quick aside, I want to talk about the second possibility here, so the photometric 0-point calibration errors, or rather the dangers of correcting for 0 points. So there's something of a mantra in template photo Z that your photo Z is only as good as the photometry you have. And the reason for this is that, of course, we're constructing a model of the galaxy which is external to our data. And so if there are calibration offsets in our data, then they're not reflected in the model, and so of course you expect biases. And also, coming from a galaxy evolution perspective, often we compile these data sets from different telescopes. So in this one case, an example using UKID's UDS. So that's the 8th data release of the JH and K data. So JH and K come from one telescope, so our UCURT on Mauna Kea. BV, RI, and Z come from Subaru, U-band from CFHT, and then the 2 channels of IRAC are obviously from Spitzer. And so all these different telescopes have different calibration uncertainties, and so it's perfectly reasonable to expect that there will be little offsets between them that can cause problems when you try to fit a template to the combined data set. And this fact is used when deriving PhotoZ for kind of high redshift and galaxy evolution purposes, to just allow these to float a little bit to improve your data with respect to this classic photometric versus redshift plot, spectroscopic redshift plot. So here are out-of-the-box easy results for a linear. The easy uses a linear combination of 6 PCA components taken from the synthetic spectra, and so in principle you can build any galaxy type in the universe from these 6 components. And so this is a really nice way of doing the PhotoZ, allowing any possible combination and trying to avoid the biases of forcing very quantized templates at each redshift. And we see that there's some problems up here in particular. So although in general the scatter is very well constrained, at high redshift the basic results that come straight out of the code are not very good at high redshift. Uncertainties, and perhaps something is driving this. And so we can apply the 0-point fiddle. We can demand that these high redshift galaxies better fit the spectroscopic redshift by changing the photometric 0 point at some of the bands. And it works, but it also destroys some of the high success we had at low redshift. And so here the problem is highlighted because we've got this wide range in spectroscopic redshift. But often you don't have these high redshift galaxies. Often you only have an abundance of low redshift galaxy. And so when you try to change the 0 points to fit well the galaxies for which you have spectra, you don't know what biases you're creating in some of the other objects. And in this case, the fact that this 0 point correction is perhaps going a little bit wrong is highlighted by the size of some of these changes. So in the U-band, the fluxes need to be multiplied by a factor of 1.4, so 40% out, which is far beyond what you might expect from simple calibration errors from the telescope and data. So maybe this is not the right way to go. And in particular, if you look at one of the objects in this high redshift set that wasn't fitting, you can see that it's not simply a case of the U and B bands being a little bit out. It's actually that the template is quite poorly fitting in general. And when we overlay the spectrum of this galaxy, because it's an optical spectrum, of course, in the rest frame, it looks pretty noisy on this plot, but you can tell that well, unsurprisingly, the photometry match the spectrum, but in particular, you see that the drop-off from the B to the U band is much sharper in the spectrum than it is in the template. And so the answer here is not to change the 0 points, but it's actually to change the allowed templates. And that's because galaxies evolve with redshift. So at high redshift, galaxies tend to have slightly steeper dust extinction laws, such as SMC-like. And so if we take that into account and we apply a blue template with a steeper dust law, then actually we get a much better result and a much more sensible, slightly more sensible 0 point offset required to match the photometric and spectroscopic 0 points here. So the lesson from this is that before we dive in and start trying to fine-tune the calibration of our photometry, we'd better make sure that the templates that we're using are reasonable, are correct, are the best that we can use. Okay, so on to what the current state of model PhotoZ are in the dark energy survey. So this is mostly work that was published in the summer. last summer in concert with the weak lensing cosmology papers that came out. And it was our first effort of doing cosmology and demonstrating that we're able to do cosmology. Okay, but to rewind slightly, we want to understand why this failure that we identified in the first part of the talk is going wrong. So to do so, we start by looking at the Redshift 0 galaxy population in the rest frame. Okay, so this is a plot by Ivan Baldry, which shows the rest frame U-R color against the luminosity. And as I'm sure is familiar to everybody, you have essentially a bimodality in the galaxy population. There's a red sequence and then a broader blue cloud. What we're assuming when we do a model PhotoZ is that we can represent these by a series of quantized templates. So we have like an elliptical, SBC, SCD, irregulars, etc. And these templates are typically fixed colors in the rest frame. So as you change with Redshift, of course, the observed magnitudes change, but in the rest frame, these colors are fixed. And sometimes we might add interpolation. So in this case, I've just interpolated one template between each, but we can use as many as we like in that to try and fill out the color space that's missed due to the quantization. But in all cases, we actually produce regions of allowed color space or color luminosity space that actually don't contain galaxies. And this isn't really a major problem in the data-rich regime because the multidimensional space of all the different colors rules these galaxies out anyway, but via the chi-square. But where we have very little information, where we only have 4 bands, then these can crop up as spurious solutions in Redshift. So if we transform this around a little bit and look instead at two different bins in observed magnitude, so that's 20 to 21 in the upper panel, 22 to 23 in the lower. We look at the rest frame U-V color against the PhotoZ. So in this case, it's Cosmos PhotoZ from the recent catalog by Legel et al. And although it's not perfect, Cosmos PhotoZ are extremely precise. And so we can use this as an almost truth for this test. And what you can see is that in this rest frame color versus PhotoZ space, the population almost inverts over the space of 2 magnitudes. So 2 magnitudes is less than a factor of 10 in brightness of stellar mass, and yet the galaxy population is completely different. And this isn't taken into account in our template run at all at the moment. So training methods, of course, capture these forbidden regions automatically because they're just not sampled by the training galaxies that go into the PhotoZ computation. Whereas for template codes, we have to apply a prior. Okay. And a prior, of course, is a very common thing in model-based PhotoZ. Almost all codes will accept a prior, and often they have ready-made ones that you can just use. Okay. So this is not doing anything special. The BPZ run that we did in science verification, or actually Carles Sanchez did, so he calibrated the prior using the available spectroscopic redshifts. So this is a direct calibration of the 11-parameter model that BPZ takes, which is based on a mix of 3 different galaxy types. So you have essentially ellipticals, normal star-forming galaxies, and then the irregular, the lower mass, the messy, kind of bluer star-forming galaxies. And then this mix of types is parameterized as a function of observed magnitudes, which takes an exponential form. And then within each type, there's a magnitude-dependent redshift probability function, which is also exponential. And so in this way, the flexible prior encompasses 3 dimensions of type, magnitude, and redshift. And so once this is calibrated using the available spectroscopic redshift, you can see that the degeneracies are very much reduced, and yet clear features remain. I'll come on to that in a second. And it's worth pointing out here that by using the available spectroscopic redshift to calibrate the prior, we're in a way doing something quite similar to machine learning methods. We're ruling out areas of color magnitude space based on a training set. And so actually we suffer from the same weaknesses or similar weaknesses as machine learning. It's not quite as direct because it's a parameterized model rather than a direct calibration. But nevertheless, this is already on the way to a hybrid method rather than a pure modeling method. And so when we do this, and we look at how the stacked probability density function for the sample of galaxies that we want to go into the weak lensing analysis looks, well, you can see on the second panel down, this is the BPZ result. So in each case, the spectroscopic redshift distribution is weighted by the inverse sampling of the spectra with respect to the parent weak lensing sample. So essentially, galaxies where there are fewer spectra for compared with the target sample have their contribution upweighted, and vice versa. So we're in regions where we're oversampled, each of those is weighted down. And on the same plot in ANZ, Skynet, and TPZ, we show 3 different machine learning codes. And you see that the 3 different machine learning codes broadly manage to reproduce the spectroscopic redshift distribution, whereas BPZ has this kind of offset and this very sharp peak at redshift 0.4. So although we've removed most of the degenerate solutions, we've actually not solved the problem, because what we want is the mean redshift of these stacked PDFs to be correct within, well, preferably 1%. As you'll see later, we don't quite achieve that just yet. And so we need to apply some kind of correction. We need to improve BPZ somehow. So despite the fact that we've used a data-driven prior that's somewhat similar to applying a machine learning algorithm, the model is still wrong. So the prior reflects the galaxy population, but the SEDs, the model underlying that, does not. And that's because the templates don't account for the fact that similar galaxy types actually have different colors depending on the luminosity, and it doesn't account for the redshift evolution of galaxies. So if you look at the bottom panel in particular, the change in the red sequence between redshift 0, which is the solid line, and redshift 1, which is this dashed line, is of order 0.1 in color, and it's even greater for star-forming galaxies, and we'll come on to why that is in a moment. And in addition to this, there's incomplete coverage of galaxy types. So another way to display that is on this color diagram. So the density histogram in the background, and also the red solid lines, solid contours that outline it. This shows where the number density of the target sample, the weak lensing galaxies, lie in this color space. And over on top of this, the black lines show where the basic BPZ templates lie. So you can interpolate in your mind between these templates and you can kind of construct what the expected envelope of allowed colors would be according to the templates. And you can see that there's some missed regions of color space. So one in the upper left, which is not a major problem, but there's also this large one in the lower right, which is highlighted on this figure here. So if we look at the regions of the BPZ templates that lie around this 0.4, where we're finding this sharp feature, we see that they construct an outer envelope of the allowed colors of the templates. And so any galaxy that lies to the lower right of this envelope is likely to end up with a strong peak at 0.4. And this is not physical. This is not true. This is just that the allowed template types that we've included don't fully cover the actual galaxy color space. And so we get this spurious enhancement of the probability at redshift 0.4. Now, okay, so the model is incomplete, and this leads to biased results. Now we understand that we're applying a model that is not quite correct, and that we will get a bias because of that. And so we can attempt to correct for this bias by using another model that we believe better reflects the underlying galaxy distribution, but is maybe impractical to include in a full photometric redshift code, and correct for the results that way. So what we did was to run BPZ on an n-body simulation that has image simulations on top of it. So each galaxy is assigned a color according to the color density relation. And from that color, we draw a galaxy type, or from the simulation, a galaxy type is drawn. And an image is simulated, so we have entire fake skies. And then Sectractor is run and the photometry extracted in the same way as is done for the real data. So in this way we have a simulated data set that has the same kind of characteristics as the real data in it. And we run BPZ on that. And because we know the redshift of each of the simulated galaxies, we can see what offset we're getting due to this bias in our modeling of the photo Z. And we reduce this down to a weak lensing-like sample using the parameters from source extractor, and explored various different methods to map the probability distribution function that we get from the simulation and from BPZ to make them match. And the best thing we came up with was a simple offset in the end of 0.08 in delta Z. So we just essentially translate the n of Z that comes from BPZ up to higher redshift by 0.08, and this was enough to align the means in the simulation. So we apply this to the data, and this is the final result from the summer. The lines show the mean redshift in each case, and you can see that the blue vertical line that represents the mean of BPZ is now nicely nestled amongst the spectroscopic or the training methods and the result from the Cosmos photo set as well. And so the final answer we had was that by correcting for this model bias using the simulation, all the different methods of getting an idea of what the redshift distribution is, or the mean redshift of the probes that are going into the weak lensing, agree to around 2%. Or 5% when we split it into tomographic bins. So this is not too bad, but as I said at the start of the talk, we need to get to 1% in tomographic bins for the final DES the final DES weak lensing sample. So at the moment we're at 5%, so we're quite a long way out. And this was just enough to not dominate the error budget, so we were still statistics limited here. But if we don't improve this in the next few years, then our cosmology results will be essentially photo Z limited, and we may as well not bother doing anything beyond 150 square degrees. So this is the challenge that we're set, and so the next steps are to improve the templates and the prior to capture galaxy evolution properly. And so from here on, rather than results, I'm going to be showing mostly work in progress and things that we need to be doing in the future that we've barely even started yet, I suppose, in some cases. But firstly, to think about the templates, we can either correct them, we can either produce new templates empirically or synthetically, and I'll show you examples of each case. So firstly, empirical. The Coleman-Wu and Wiedemann set of empirical templates that are used in many template codes have been very successful. And they're constructed from a set of redshift 0 galaxies. So they ought to be pretty much correct. However, they don't capture the evolution with redshift. And so it's actually this redshift evolution that we want to try and replicate by producing new templates. And so what this implies is that actually we just need to morph and modify the existing templates to better fit what galaxies look like at higher redshift. So we run at fixed redshift a code to find the best fitting Coleman-Wu and Wiedemann template for a set of Primus galaxies. So Primus was this this slitless spectroscopic survey which went down to I of 23. But because it was slitless and because it was using automated redshift determination, there's a small fraction of the galaxies that actually have wrong redshifts. And so we can't use it in the traditional training and validation scheme, and also it has a sharp cutoff at high redshift at around 1.18 in redshift. So again, it can't be used in the training of machine learning methods, but we can use it to look at how the templates evolve with redshift. And so what we use here is the fact that as we move to higher redshift, a given observed band samples the rest frame wavelength at a slightly different wavelength. So if you take the photometry and then shift everything down to the rest wavelength, you find that the galaxies in a range of redshifts are sampling it at different places, and that's what's shown on this bottom plot here. So in green is the G band, and then grey, pink, and cyan we have R, I, and Z. And so of course the left-hand limit in each of these colours is the highest redshift galaxies that were allowed in that range, and vice versa. The right-hand limit is the lowest redshift. And so you can see if we construct, if we use a sample over wide enough range, then we can get these different bands to overlap, and we can construct a median offset at each rest frame wavelength, which we can then use to correct out the template. So the most obvious feature is this dip around 3,500 angstroms, and this is exactly what we expect. So this is telling us that that the template needs to be brighter at 3,500 angstroms with respect to the redshift 0 one that we're putting in. In other words, the strength of the 4,000 angstrom break needs to be reduced. The template needs to get bluer. So this is just what we were showing with the evolution between redshift 0 and 1 for D2.
Will?
Yeah?
You can try to use your mouse as a pointer to show.
Ah, okay. Oh, yeah. Sorry, I didn't think of that at all.
Okay, thanks.
Okay, so yeah. So you can see if you follow the median, we're at roughly 0 for most of the template for the optical regime. But then as we approach the break, we find that we need to make, we find that there's a clear offset between the photometry that we require and the photometry of the template. And so the template in this case, this elliptical galaxy at intermediate redshift needs to be bluer. And another example is the SBC type galaxy at even higher redshift. In this case, there's a bit of a slope also to the offset that needs to be applied. So this is actually telling us, I think, that the redder tail, where the stellar mass is more sampled, needs to come down slightly, and then again the kind of the rest frame UV needs to be brighter. So things are forming more stars. Star-forming galaxies have a higher specific star formation rate at high redshift. So this is the idea, that we can correct out the templates in different redshift ranges just empirically using these Primus data that we're not using for something else. However, it's unfortunately not quite as simple as I've shown. So in practice, the wide redshift intervals are not ideal, and that's shown on this plot here. So we have again the magnitude offset on the y axis, but now I've put redshift across on the x-axis, and instead of limiting the galaxies that I'm looking at by a redshift range, I've instead limited them by a rest frame wavelength range. So I've picked out only those data points, those rest frame bands that pick out this range in wavelengths. And you can see that there's this kind of a strong dependence in each case. So there is there's redshift evolution within the wide redshift intervals that I was considering before. And so what we really need to do is to fit a function between, say, the red points down here, these red ones, these ones, and these ones. You can see we'll have, generally speaking, a kind of a quadratic-like change, and likewise for the green and all the other colors. we want to fit this kind of function so that we can correct the templates in a 2D manner. So not only with wavelength, but also with Redshift in a continuous way. And we do this for each basic template. And as an extra bonus, we get a scatter at any given Redshift and fixed rest frame wavelength. And this tells us how the kind of dispersion in the galaxy types that are fitting that template. And so this gives us an idea of the systematic uncertainty that we might need to apply to the photometry in order to improve the chi-square precision. Okay, so when we've done this, when we've shift and wavelength dependent way, and we can run them through again using a Redshift code. In this case, I've chosen Zebra, and that's really just for operational reasons because it was easy to implement Redshift dependent templates in Zebra, whereas it's less so in BPZ. And so this is using DES Y1 data, where the depth is not quite as good as science verification because it's not been built up yet. It goes down to around 23. Zebra applies an internally calibrated prior, which can go wrong sometimes. It assumes that your first solution is pretty good and then kind of reinforces that in a way. And so I split it into two magnitude bins to allow that to work a little bit better. The flexibility of the BPZ prior is superior, so eventually we'll need to apply an external prior to improve these results. Overall, the bias is improved with respect to what we had with using just the basic templates. The degeneracy, well, kind of exists here, but it's not too bad. It also exists a little bit here. In fact, these objects, these I greater than 22, are very faint, and this performance is not bad at all, considering how faint they are. And these degenerate solutions will be reduced even further by using an external prior. More importantly, the Redshift 0.4 feature is absent in this particular case. Well, it's clearly down here in the faint galaxies, but well, it's not the only one here. There's a little bit of work to do to eradicate some of those. But again, these are reinforced by the internal calibration of the prior. So again, these are not going to be a major problem once an external prior is imposed. So this is somewhat encouraging. It looks as though we can adapt current templates and get some level of performance boost. And if we apply the same machinery that we have done to BPZ in the science verification analysis, then perhaps we can get some distance with this. So that's one way of empirically changing the templates to try and improve performance, but it doesn't really include any additional information externally from what we know about how galaxies populate the universe, how they evolve. And so the other stream is to look at, okay, I don't have long left, towards synthetic templates and try and get more realistic templates this way. So the classic implementation of synthetic templates in PhotoZ is to use exponentially declining star formation histories that have been very popular for many, many years in determining stellar masses of galaxies. And these typically require a single metallicity per template. They have a range of allowed ages, and the only real limit on what can be fit is the age of the universe at the redshift at which you're trying to fit the galaxy. Otherwise, all the templates are allowed, and in addition, of course, the usual things like intergalactic extinctions are applied. So similar to empirical model methods, they're generally good enough when you have a lot of data, but these templates don't really reflect our current understanding of galaxy evolution. We know that exponentially declining star formation histories are not really correct. We also know that the galaxies changing, that the stars are formed with different metallicities at different times during a galaxy's life. And so we want to incorporate all of these extra little bits of information into the templates and see if we can improve things. So here in 3 slides, I suppose, is a summary of what I would say is the most accepted picture of the galaxy, of the evolving galaxy population. And it starts really with this paper from 2007 by Kainoesk. And he found that when you look at different redshift intervals, if you look at the star formation rate of star-forming galaxies as a function of stellar mass, then you get a relatively tight relation. So there's only scatter of around 0.3 dex in this simple linear relationship between the star formation rate and stellar mass. But more importantly, the normalization of this relation evolves with redshift. So as we go from low to high redshift, we increase by a factor of 10 to here. By redshift 2, it's a factor of 20 higher. And so if you're a galaxy on star-forming sequence, say around about here, at this redshift, of course you form stars and so you increase your stellar mass. But then as you go down in redshift, you see that your expected star formation rate has declined. And so you can trace galaxies down as they build stellar mass, what you expect their star formation history to look like. And so this has kind of become known as the main sequence of star-forming galaxies, how they're contained to this this relatively tight relation, and has really set up a lot of the progress in recent galaxy population studies, and now it's pushed all the way out to redshift 4-ish. The second important thing that I want to talk about is actually how galaxies finish forming their stars. So near-infrared surveys such as the UDS and in particular UltraVista in this case have allowed us to study the stellar mass function of star forming and non-star forming, the kind of quiescent galaxies, out to very high redshift, out to redshift 4 now. Now there's an asterisk there to tell you that this is obviously subject to sample variance because these are always on very small fields of order a square degree or 2 square degrees at most, and so there's some uncertainty into how much the normalization changes with time. However, the most striking thing actually is that the shape of the star-forming stellar mass function doesn't really change much. The normalization moves up with time as you get more and more galaxies, and as galaxies build stellar mass. But for star-forming galaxies, you always have this same exponential cutoff. Now, of course, if a galaxy is forming stars at high redshift, at redshift 2.53, where the pointer is, then it's going to move along to higher mass along this way. And so, as you go to lower redshift, this kind of implies that the galaxies that are forming stars at some rate must leave this diagram. They must join instead the quenched population. And so, between the main sequence from the previous slide and the star-forming mass function here, these 2 results led Peng et al. To define the form of mass quenching. So this is the phenomenological way to describe how galaxies end their star formation due to processes that are related to the stellar mass of the galaxy. And so now we can describe the star formation history of a galaxy almost in entirety. So starting from high redshift, how it builds up stellar mass and eventually turns off. And then the final key piece of information is in the metallicities of galaxies. So the metallicity of the gas that goes into star formation is a function of the galaxy's stellar mass and the star formation rate. And this forms a 2D surface which appears to be independent of redshift. And this has become known as the fundamental metallicity relation. So whereas before, using these exponentially declining templates with a single metallicity, it would be very easy to assign to a galaxy an unphysical template, say a high metallicity for a high specific star formation rate or low mass galaxy, things that don't exist in the real world. And so by using these 3 pieces of information, what we can try to do is construct a self-consistent redshift knowing set of synthetic templates. And so we follow this main sequence as it evolves. We quench them according to Peng et al. 2010, and we form new stars at each stage with respect to this fundamental metallicity relation. And then when it comes to running the photo-Z code, we only allow templates to be fit at the appropriate redshift. And this is what 3 examples of this sequence looks like. So on the left there are stellar mass in linear and log space, and each of these is simply a galaxy formed at a different point. On the right you see in the upper panel how the star formation rate changes with time, so it builds up exponentially very quickly and then declines as it quenches and falls off. Whereas the green and blue galaxies here continue to form stars. They don't quench, but as they track the star forming main sequence, their initial rapid increase just falls off and starts to come down. And likewise, you can trace the gas phase metallicity in the lower right-hand panel. Okay, so we have a set of 80 templates at each redshift, and each template is allowed at that redshift only. So there's 80 at redshift 0.01, 0.02, etc., etc. And then we perform chi-square fitting, and we get something that looks like this, which is not exactly inspiring. But I should remind you that no prior has been used yet. So there's nothing to forbid the degenerate solutions that come not from the fact that we're using wrong templates, but from the fact that you can have a very bright galaxy which is very blue. So the normalization is still free. And so again, when the prior is included, that should kind of fold out those issues, and hopefully things will look a little bit better. But there are also some known calibration issues with synthetic templates that need a little bit of work as well. Okay, so I'm close to out of time, I guess, or past time. So this is very quick, so I may as well dash through this. Constructing the right templates is only half of the battle. So a template is a model of a single galaxy, but we also need to include in the model the model of the entire population. So to restrict which types of galaxies are allowed in a sense, but also so that we construct at the end a realistic sample of galaxies. And the prior fundamentally comes from the galaxy luminosity, or in the case of synthetic templates, you can also use the stellar mass function. Different luminosity at different redshifts. So these data are from the UKIT UDS, work done by Michele Carasuelo. And this is probably still the state of the art in terms of luminosity function analysis. And this one goes out to redshift 1. And the reason for that is that in galaxy evolution, luminosities have somewhat fallen out of favor, and people are more interested in stellar masses. So the stellar mass functions, as I said before, go up to redshift 4 and are useful for synthetic galaxies. But for empirical ones, we can only use the luminosity function. So that's what's shown here. So the observed magnitude implies a different luminosity at different redshift. Interested in, and so these multiplied together give you the expected abundance of at different redshifts of your observed magnitude, and as I said, this can be used for both empirical and synthetic templates. And of course, you can include further information in this as well. The real problem here is that you can only really produce these kind of observed luminosity functions down to high completeness, where you have very rich data, and either your spectroscopic samples are incomplete, which is a problem, or the high quality photo-Z that go into them are on very small scales, and so we always have sample variance issues. And really, there's just not been the will to produce luminosity functions . these are a few of the challenges that lie in the way, but none of these problems are insurmountable, and so there's potential for a lot of improvement in this area to come. Okay, so I was going to finish with a quick discussion of red magic, but I think I've run to an hour. So should I end there, or?
No, please go ahead, Will.
Okay, all right, thanks. Okay, so a lot of what I've shown in the last 20 minutes have been kind of work in progress and encouraging steps in the right direction. But there's already one example of this in practice to a degree, and that's called red magic, which is developed by Eduardo Rosso and Eli Rykov. And the idea here is to focus on the galaxies that it's easiest to get very good redshifts for. And so they use a single empirical template for the luminosity and redshift dependent red sequence. So this actually comes out as a byproduct of a cluster finder. So one way to find clusters in the universe is to look for distinct red sequences. And as you push to higher redshift, of course, this changes in your observed colors. And so they actually don't even create a template as such. They use the direct calibration, but from the data, not using spectroscopic redshifts in this stage, but from the photometry itself in the cluster findings. So they're using the physics of the fact that clusters have lots of galaxies that are no longer forming stars to get the correct description of the colors for those galaxies. And they also include a prior on the form of the luminosity function, not the normalization, but just demand that it is a Schechter function, and that turns out to be more or less enough. Now the redshift range that they can do this over, of course, is limited by the cluster finder, because that's where the calibration comes from. And so at the moment it's currently limited to redshift 0.8. They do intend to extend it a little bit further, but obviously for weak lensing, that's not really sufficient, because the tail to high redshift needs to be known. However, this is an extremely useful sample for various other things already. Once the basic solution is made, they can also use spectra to refine the solution and better understand the errors. So this is really a complete solution from what I've been talking about for one type of galaxy, these red galaxies. So it involves redshift and luminosity sensitive template and a physical prior on what the distribution of these galaxies should look like. And so here is how it performs. In the left-hand plot, you see this traditional spectroscopic versus photometric redshift, where the grayscale is essentially contours, and then the individual outliers are each points, which does extremely well. But more interesting is the kind of summary statistics on the right. You remember that for DES, the bias needs to be within 0.01, so it needs to be within 1%. And almost across the entire redshift range this is true, but also the scatter is extremely well characterized. So using the spectroscopic redshift, you can measure what you expect the scatter to be, and the model actually comes up with a predicted scatter too, and these lie bang on top of one another. So when you get the galaxy model correct, the prior and the templates, then actually the redshifts can be good enough. Our challenge now is to extend this to a more general solution. As I said, the red galaxies are the easiest ones to do, and we now need to include or come up with a solution that includes all the blue galaxies as well. So just to finish with the take-home points. Requirements on the photo-Z accuracy and precision in cosmology experiments are a considerable challenge. And due to the spectroscopic incompleteness in the data sets and what will continue to be likely in the future, it's really the case that modeling approaches to photo-Z have to work. Traditional templates and prior calibrations were good enough for DES-SV with a bias correction, but they won't be for anything in the future, for year one, for the final DES or for any of the other experiments that are coming up. And so we need to get improved templates, either via empirical and synthetic methods, together with appropriate priors to really make progress in this area. And there's some distance to go, but there are some encouraging signs, particularly in the success of the Redshift solution, which demonstrates that actually it is possible. And I will stop there. Thank you.
Thank you. Okay, thank you, Will. Great comprehensive talk. I guess we have time for a few questions. Aurelio, please.
Hello, Will. It's Aurelio.
Hi.
So, what about, or have you started thinking or working, combining neural networks and template fitting? Because I guess that some cases one are better than the other, but could not be combined in a single algorithm or in a single estimation?
Yeah, so so there are various people looking into hybrid approaches, and I have put some thought into it as well. Maybe well, you know Ben Hoyle. He's interested in augmenting machine learning methods with template approaches. I actually take a slightly different look at the problem. So I won't go through this, but the idea here is that you have a traditional kind of template fitting approach that gives you a probability distribution, and then you use the spectroscopic redshift information to help inform a better prior, and then you get the posterior and the PDF out. So yeah, absolutely. I think that the template codes are obviously underusing the spectroscopic information at the moment, particularly if we want to avoid using them to kind of directly calibrate the prior. So there are a few options here, and yeah, I think it's a fantastic way to go.
Okay, cheers.
So I guess I have one question. So you mentioned, I guess you focus on galaxy evolution prior, which is perhaps more important, but do you plan to include some extinction prior, some kind of law, how the extinction would vary as a function of redshift, for instance?
So I didn't mention this aspect. Extinction is applied to the templates. Do you mean the extinction from the galaxies themselves? Yeah. And I've applied it at the moment by the stellar mass of the galaxy.
Okay.
So I'm not sure what the right way to go with this is. We know that more highly star-forming galaxies tend to have higher extinction, but then star formation and mass correlate, and there are conflicting results in the literature at the moment as to whether the extinction should key off the star formation rate or the stellar mass. I've put it in on the stellar mass, but yeah, that's a very important aspect that needs to be modeled somehow.
Oh, okay. You mentioned you use Primus, and you also mentioned how it's bad for training. So how did you get rid of the bad Z's?
So actually I didn't. We estimated that the fraction of wrong redshifts is of order 4 or 5%, I think, or maybe slightly less. So it's not too bad, but it's not good enough to be used in training a neural network or something like that. However, in correcting the templates, because I can use the median, I kind of assume that the outliers are going to scatter and just be outliers, so they can be clipped out, and so the wrong redshifts actually shouldn't affect the correction of the templates to different redshifts.
Okay. More questions? Actually, I have one. This Tanaka and Chevalier and Charlot templates, are they available online?
So they're not templates as such. They're more kind of methods. The Shabala one is not, I don't think. No, they intend to make the code public eventually, and actually Tanaka is the same. So he's writing his own code, which is called Mizuki, and it's not public yet. But I guess you can keep an eye on.
All right. Do you have a question for?
Are you going to the meeting? This meeting?
I am.
Yeah.
I am. Yeah.
Fortunately, none of us is going. So.
None of you.
Well, Luis is.
Our.
You can chat with Luis.
Okay. Okay. Good.
Okay.
And then the rest.
Yeah,
so go ahead.
Fortunately, economic in Brazil is not very good now, so.
I know. I've heard. Yeah.
The dollar exchange is a bit.
Anyway.
And Stanford is expensive even for us. So.
Really?
Oh yeah, it's crazy. It's the